All right, so today, pretty straightforward. We're just going to continue on with operations on polynomials, talking about dividing monomials, and then we'll start dividing polynomials, and we'll probably finish that up next class, and just continue forward with chapter 6. The quote of the day today is by the Roman Emperor Marcus Aurelius, one of the Stoic philosophers, and Stoicism's becoming more of a big deal these days. So this quote is making the rounds. It's usually just quoted as B1, but it comes from this line here in his Meditations, his book Meditations. Stop arguing about what it means to be a good man, B1. So it's easy to kind of sit in the comfort of your living room and debate about what a good person should do in this or that case, but actually putting putting one foot in front of the other and making it happen is really where it's at. So I think that's what he's trying to say here. Okay, so moving into dividing monomials and polynomials. So let's take a look at a very simple example of dividing monomials. We said that really a monomial is just anything where there's just one term with constant times variable to a power. And actually just a constant, just like the number 16, well, that could be a monomial, or the number 4 could also be a monomial. So 16 divided by 4, just a MAT090 problem, an arithmetic problem, we could think of as a division of monomials. And we could think of some things that we might be interested in doing with this. One thing we might be interested in doing is seeing if there are any common factors. In other words, maybe I realize that there's a factor of 2 in 4 and a factor of 2 in 16. Or I might even realize a little bit more of that there's a factor of 4 in 4 as well as 16. But I could think of breaking, say, a 2 off of the 16 into 2 times 8, and breaking my 4 into 2 times 2 and dividing out a common factor. And I can think of maybe doing that process again. And maybe in the denominator, instead of writing 2, I'll write 2 times 1, just to remind myself that I still have that denominator of 1. And then, of course, 4 over 1 is just 4. Or if I were to write this a different way, I might be able to write it as something like, well, 16 it has a prime factorization of 2 to the 4th power. It's 2 times 2 times 2 times 2. And 4, well, 4 has a prime factorization of 2 squared. And maybe I can use a property of exponents here. So give me 1 second. My trackpad has some stuff on it. There we go. Maybe we can use a property of exponents here. And we had a property that said x to the a times x to the b equals x to the power a plus b. But we can combine this together with another idea that what is a negative power? X to the negative a equals 1 over x to the a. So like, 2 to the minus 3 power would be 1 over 2 to the 3rd power. And this means that x to the a over x to the b is like x to the a times x to the minus b, or that's x to the power a minus b. So I see really where I'm getting this extension from, these next couple ideas, is really from this basic idea of breaking the numerator into prime factors, breaking the denominator into prime factors, and then dividing out common factors. Or I could think of this as 2 to the power 4 minus 2, or 2 squared, or 4. So I get to the same place, but I can do it a little bit more efficiently. Maybe if I use some exponent rules, than if I were to say just keep breaking off individual, say factors of 2 in this case, and dividing them out. And I can generalize this idea to variables. So I have x to the fourth over x squared. Implicitly, we're here assuming x is not 0. Otherwise, that x squared in the denominator would cause a little bit of a problem. And I could do a similar thing here. I could either write this as like x times x times x times x over x times x and divide out 2 of these x's and get x times x or x squared. But we can see that's pretty cumbersome. That's a lot of work. That's a lot of stuff to write out. But I could also use an exponent property, x to the 4 minus 2 or x to the second power, and get the same answer a little bit more quickly, a little more efficiently, probably a little less error prone. So I can make use of these exponent properties. Now, what if I have something like 3 divided by 27? Well, this is like 3 to the first power, and 27 we might recognize as 3 cubed. If we didn't, if we were thinking, is it divisible by 3? 7 plus 2 is 9. Since the sum of the digits is divisible by 3, the original number is divisible by 3. So this turns out to be 3 cubed. And now again, if I use my exponent property, 3 to the power 1 minus 3, taking this first power from the numerator and the minus the third power from the denominator, gives me 3 to the negative 2 power. And remember, that means 1 over 3 to the second power, or 1/9. Now, of course, in a problem as simple as this, it probably would have been quicker to just divide out a factor of 3 from the beginning. But we now understand something a little more generally, and we can apply that to a problem like, say, this one, y to the third over y to the seventh. And see that's y to the power 3 minus 7. Which is y to the negative 4 power, and which is 1 over y to the fourth power. One that likes to turn my 4s into 9s if I'm not really careful about how I write them. And we see implicitly still y cannot be 0. Otherwise, we'd end up with a 0 denominator. Okay, so 2 super quick exercises here. Take about 60 seconds or so. I'm actually going to zoom this in just a tad, make it a little easier for you to see. Take a look at these 2 exercises. I'll give you about a minute or so to complete these 2 exercises, and then we'll go through the answer. So we'll come back in about a minute. Okay, it's just about a minute. So pretty straightforward exercises. We're just getting kicked off here, so X to the 7th over x squared is x to the 7 minus 2 power, or that's just x to the 5th power. And we can see that also if we divided out two factors of x from the denominator and the numerator, we'd have 5 left in the numerator. We see that that's concordant with what we got using the exponent property. And p to the 5th over p to the 9, that's p to the 5 minus 9 power, or p to the negative 4 power. And we rewrite that as 1 over p to the 4th, where again, p cannot be 0. Okay, so one special case that we might be interested in is, what if I have the same number of factors in the numerator as in the denominator? Well, what if I have something like 3 to the 1st power over 3 to the 1st power? That's 3 over 3, or that's 1. So we pretty clearly know that 3/3 is 1. But on the other hand, I could think of this as 3 to the power 1, the numerator power is 1, minus the denominator power is 1, or that's like 3 to the 0 power. Or what if I thought of like x over x, again, where x is not 0, so the denominator is happy. But if I thought of x over x, well, what is x? It's just a placeholder for a number. So x might be a number like 3. We might get like 3 over 3, or it might be a number like -2, -2 over -2. That's also 1. It might be a number like 17/6. Well, 17/6 divided by 17/6 is also 1. In fact, x over x, on one hand, we could write it as x to the 0 power. That's x to the 1 minus 1. And on the other hand, we see that it's always going to be 1, so long as x is not 0. So x to the 0 power is 1, or really anything to the 0 power is 1, except 0. As a little aside, 0 to the 0 power is what we call indeterminate. It kind of means that it could be anything. It's not clear from just writing the notation 0 to the 0 power what that means. And when I say it could be anything, I mean that it's context dependent. I mean, you could come up with a problem where 0 to the 0 power seemingly ought to mean 5 or ought to mean -4 for a different problem, or a different context that might mean, 17 halves. So 0 to the 0 is indeterminate. It can mean different things in different contexts. But anything else to the 0 power, any non-zero number raised to the 0 power, gives me 1. And this is kind of why, because the 0 power we can interpret as kind of the numerator having the same number of those factors as the denominator. And if the numerator and denominator just represent the same thing, well, then I have something over itself that's 1. So again, I could represent 3/3 as 3 to the 0 power, which is 1, or x to the 0 power is 1, so long as x is not 0. The x not being equal to 0 is kind of a minor detail. The important thing is that when you see something to a 0 power, that's just 1. There's some like math joke like t-shirts or things that are like, it says like your number, like you are number, and then it has this like big long expression. It has all of this, crazy stuff inside of parentheses, and you're like, how am I ever going to calculate that? But then it's to the 0 power. And so long as you can tell that the stuff inside parentheses is not 0, then it's like you're number 1. So, uh, we don't have a lot of fun jokes as mathematicians, so we got to kind of work with what we've got. All right, so what about something like this? 2/3 to the 4th power. I have a distributive property of exponents over multiplication. Let's say x times y to the a equals x to the a times y to the a. And I really have the same thing over division, right? 1/3 is just kind of like 3 to the minus 1 power. So x over y to the a is x to the a over y to the a, or we could think of it as x to the a, y to the negative a. So 2/3 to the fourth, I could on one hand think of this as like 2/3 times 2/3 times another 2/3 and times a final 2/3. These fractions are all multiplied together, which means I just multiply their numerators. You get 2 to the fourth. And then I multiply the denominators. That's the new denominator over 3 to the fourth. Or that's 16 over 81. 3 to the fourth is like 3 squared squared. 3 squared is 9. 9 squared is 81. And now I can think a little more abstractly. If I have something like r squared s cubed over rs squared, that's all raised to the third power. How can I simplify this? Well, one thing I might be able to do is, say, take my numerator to the third power, divide that by my denominator to the third power. And now I can use my other distributive property, x times y to the a is x to the a times y to the a, or I have r squared to the third times s cubed to the third. And that's all divided by r to the first to the third, or that's just r to the third times s squared to the third. And now I have a bunch of power to the powers. Remember that x to the a to the b power is x to the power a times b. So when I have a power to a power, I multiply the powers together. So this is r to the power, 2 times 3 or 6, times s to the third power, or that's s to the 3 times 3, or s to the 9th power. That's divided by, well, that r cubed is just r cubed times s squared to the third power. So that's s to the 2 times 3, or s to the 6th power. Now I can kind of break these back up into like r to the 6th over r cubed times s to the 9th over s to the 6th. And I see that for my r's, I have r to the 6 minus 3 power. And for my s's, I have s to the 9 minus 6. Or that's r cubed, s cubed. Now I can do this, it works. That was quite a bit of work though. I could actually make life quite a bit easier for myself. Yeah, let me try to get a couple more lines down here. I can make life quite a bit easier for myself if I look at this problem and say, okay, before I start breaking things apart and applying exponent properties, can I simplify things a little bit first? So let me take another look at this problem. R squared s cubed over r s squared, all to the third power. So again, we could just mindlessly apply our exponent properties, go through the process. We get there in the end, but can we be a little more efficient about it? Can I cut out maybe some of these intermediate steps, or at least make them a little bit easier, make the numbers a little bit smaller? And actually this, at the end here, this what was it, second to last step, gives me a bit of a hint. I have actually a lot of cancellation here. There's a lot of common factors that divide out. Can I actually look at that before I start distributing my exponent? Can I look at this inside of the parentheses, this r squared s cubed all over rs squared? Does anything divide out here? Well, actually, yes, I actually get a decent bit of simplification here. R squared divided by r, that's r to the 2 minus 1 or r to the first power. So that takes care of the factors of r in both the numerator and denominator. This just r to the first power is all that's left over. And s cubed over s squared, that's s to the 3 minus 2 power, or just s. My inside of my parentheses turns out to just be r times s. That's a heck of a lot simpler than this r squared s cubed over rs squared. And what's r times s all to the third power? That is r cubed times s cubed. That was a heck of a lot quicker, right? I always want to look for ways to decrease complexity before I increase it again, right? I always want my complexity pattern to look like a sawtooth, right? I simplify, decrease complexity, and then I do an operation, maybe a distributive property that increases complexity again, right? And then I simplify as much as I can to decrease complexity before I do another operation, increase it again. The difficulty of a certain operation or whatever typically scales non-linearly with its complexity. So if you make something, twice as complex, it's probably 4 or 8 times as difficult to deal with. So by simplifying on each step, that really makes things much, much easier for me to do. It makes it a lot less error prone, and there's just actually less stuff for me to copy, less just kind of simple errors like just copying the wrong thing from the previous line. So we always want to see if we can simplify anything before we apply a property, right? So I looked at the inside of the parentheses, asked if I could simplify that first, and it turned out that I could simplify that first using some other properties. So before I distributed the third power, simplifying first made things go a lot smoother. I definitely got there the previous way, right? If I didn't notice that, I could have still got the answer. And sometimes, if you spend too much time looking for some little trick or some little thing that you can do to make the problem easier, all of that effort ends up being more effort than if you had just started on the problem. Or sometimes if you don't see such a trick, you get a little bit stymied and don't know where to start. So sometimes, this is the preferable route if you say, okay, well, I'm not really seeing a trick here. Sometimes just taking a step and moving forward, it's better than doing nothing, right? But sometimes you can see a simplification that can be made that can make your life a lot easier. So always worth just kind of checking, seeing if there's a little simplification that can make the process a bit easier before you just kind of plow forward. Okay, let me erase just a couple of these lines here. So here we have 5 exercises. Trying to get them all on the page. I zoomed in a little bit, so that made them run off the page a little bit. There we go. All right, so we have 5 exercises to simplify. And a couple of these are a little tricky. So I want you to really take your time on these and go slowly, particularly these first 2. You might notice the first 2 look pretty similar. Think carefully about what's being said here. When we have the 0 power here, what entity are we kind of thinking of as maybe that thing to the first power over itself to the first power, something like that. We have a y to the 0, and then a couple of simplifications down here. So take maybe about 4 minutes or so for these 5 problems. Go through them kind of carefully. think about some of the nuances. We'll come back in about 4 minutes and talk about the answers. Okay, it's just a little over 4 minutes, so let's touch base on these. So let's look at these first two. I have negative 12 to the 0, or negative 12 in parentheses to the 0. What's the difference between these? Well, let's maybe start with the second one. Negative 12 to the 0 means I take negative 12, for instance, to the first power divided by negative 12 to the first power, something like that. So I can think of negative 12 in parentheses to the 0 power as being something like maybe negative 12 over negative 12. This would be negative 12 to the 1 over negative 12 to the 1, or negative 12 to the 0. And that, of course, is the same thing over itself. That has got to be 1. But what about negative sign, then 12 to the 0? Well, this is more like negative 12 to the 1 over 12 to the 1. It's more like there being one negative sign in front of the fraction, and then that 12 to the 0 is really its own entity. It's in a similar manner to like how, say, negative x squared, this is really like negative 1 times x squared, right? This is not negative x squared. So we have to be careful with the location of that negative, whether it's inside parentheses or not. Of course, negative of, say, 12 over 12 is equal to negative 1. So on one hand, we get negative 1. On the other hand, we get positive 1. Right? We can think of this one as like negative of something to the 0 power, which is negative 1. And then negative 12 in parentheses to the 0 power. The whole thing is getting raised to the 0 power. That's just something to the 0 power, which is positive 1. So we have to be a little careful there. So hopefully you picked up on that. It's a really easy thing to miss, especially if these aren't right next to each other, but hopefully putting them right next to each other and kind of, hopefully that helped clue you into there was a difference between them and to treat them carefully. As we kind of said before, y to the 0 equals 1, but we do want to remember that we have this little detail that y should not be 0. Otherwise, if y was 0, we might be looking at 0 to the 0 and think of that as something along the lines of, say, 0 to the 1 over 0 to the 1. It might be something like that. And here I have a 0 denominator, and I'm not really sure what to do with that. Okay, then the next one, 3/5 to the third power. Nothing really tricky here. We just use our distributive property and make this 3 to the third power over 5 to the third power. 3 times 3 is 9, times 3 is 27, so that's the numerator. And 5 times 5 is 25. 25 times 5 is, well, that's like 25 times 4 plus 25, or that's 125. So we get 27 divided by 125 as the answer for this one. And then our last exercise, x cubed times y over x times y squared, all to the 5th power. And again, we saw our last example here. We could just kind of, do this the brute force way. I kind of call it the sledgehammer method, like just start, whacking stuff with a sledgehammer and see what comes out. But we could be a little bit more subtle with it, a little more careful, and realize, okay, this interior of this parentheses actually already has a lot of simplification I can do. So can I make the exponents basically smaller before I make them bigger by multiplying them by this exponent 5? And the answer is yes, I can. X cubed over x, I can either just think of dividing out one factor of x from the numerator and denominator, or I can think of using a power rule. X to the 3 minus 1 equals x to the 2, or x squared. And then for the y's, y to the 1 minus 2 is y to the negative 1, or 1 over y. So I get x squared over y, and that's all raised to the 5th power. So this interior of the parentheses just simplifies down to x squared over y. And now I do the next step. So I've decreased the complexity. Now I increase by distributing the 5. I get x squared to the 5th all over y to the 5th. And that's x to the 10th over y to the 5th. And here, actually, neither x nor y can be 0 because remember, in the original statement, x and y were both in the denominator. So even though I don't explicitly see an x in the denominator in my answer, x is still not allowed to be 0. If we think about what if I let x be 0 and let's say y be 1 or something like that, well, over here I'd have like 0 over 1, 0. That would seem to be fine. So we say, what's the problem? Well, the problem is over here I have like a 0 over 0. I don't have the same thing. I have some kind of indeterminate form or something with a 0 in the denominator that I'm saying is equal to something that is just the number 0. Those are not the same thing. So for me to be able to say with any validity that all of these equal signs are true, that these two ends, this and this, represent the same thing, I better not allow x to be 0 either. I can clearly see that y can't be 0 in either case, but I better not allow x to be 0 either. Okay, now let's start in the 6.6 dividing polynomials. So everything we looked at up here was monomial divided by monomial, single term divided by single term. Uh, Roughly speaking, we didn't see any pluses or minuses in the numerators and denominators. But here we're looking at examples where we might have more than one term in the numerator, or maybe even later on, what if we have more than one term in the denominator? Okay, let's take kind of a silly example to start with, just to illustrate the idea. Let's say we're interested in finding 18 halves. Maybe one thing I could do here is I could split 18 into something like 10 plus 8. Like 1 times 10 to the first power plus 8 times 1, or 8 times 10 to the 0 power. So I could split 18 into 10 plus 8, and I could make 18 halves into 10 plus 8 all over 2. Now I do remember that I have a property just with addition of fractions that if, if I have two fractions that have the same denominator, say in this case c, then I add their numerators. If those are fractions are added together, I add their numerators, I keep the same denominator. So a over c plus b over c equals a plus b all over c. I can do that in this direction, but I can also do it in the other direction to break fractions apart. In other words, I can look at 18 over 2 like 10 plus 8 over 2, or I could choose to look at that like 10 over 2 plus 8 over 2, and I can do each of these simplifications. Right, what is 10 over 2? That's 5. And what is 8 over 2 is 4. That gives me 9. Now, this is kind of a silly way to figure out 18 over 2, but I wanted to do this to illustrate the process. That if I have a numerator with two terms over a denominator, I can choose to break this into two different fractions where, here I basically had something that was like, kind of looked like a polynomial. It had multiple terms added together. And here, I just have monomial divided by monomial plus another example of monomial divided by monomial. I just have things look like this twice. Okay, so what if I had an example like this now? 15x squared plus 10x in the numerator, that's all divided by 5 in the denominator. Well, this looks more complicated. It is more complicated, but the steps are the same. I can do all of the same steps, same arithmetic steps, as I did up here. I can say, okay, well, I can't like combine these together as like terms, but I can still break them apart into two separate fractions. So I have 15x squared divided by 5 plus 10x divided by 5. And now I can look at each of these ratios of monomials separately. So if I have 15x squared divided by 5, in the numerator, this is like 3 times 5 times x squared. In the denominator, it's like 5, or just 5 times 1. And I see I can divide out a factor of 5. And I see this all comes down to just 3x squared over 1, or that's just 3x squared. So that was for our first parentheses, our 15x squared over 5. And now we need to deal with the 10x over 5. So 10x divided by 5, well, that 10 I could write as 5 times 2. I still have a factor of x in the numerator and 5 in the bottom. And again, if I really wanted to, I could write this as 5 times 1 in the bottom. And I can divide out a factor of 5, leave me with 2x over 1, or just 2x. Now, at this point, I don't have like terms. I can't combine anything back together. But we can kind of see how here's like where we started. This was our intermediate step. And then our final answer just kind of ended here. So even though we have a polynomial in the numerator, the operations that we're doing feel pretty similar to what we would do if we just had constant terms like this. And if we decided to divide them or to simplify things in this manner, which maybe is a little silly, we normally go the other way and simplify 18 halves directly to 9. But if we went this kind of longer way around, there's nothing objectively wrong with that. Might be a little less efficient, but we can do it with a case where we just have all numbers, all constants. But that's the approach that we take when we have variables. We kind of need to go that slightly longer way around, break the fraction into individual terms that are each monomial divided by monomial, and then simplify each of those. Okay, how does this change if instead of, say, having a constant in the denominator, maybe I have a variable in the denominator, 15x squared plus 10x all over x instead of all over 5? Well, one thing that changes is I kind of see I have to be careful about my denominator. I probably ought to note somewhere that x should not be 0. Otherwise, this denominator is 0, and that's problematic. Is there anything else that really changes? Do I have a common denominator that I can split up? Well, yeah. X is just a placeholder for a number. If that was over 3 or over 5 or over -2, I could split those fractions up just fine. I can split it up with an x in the denominator just fine. So I get 15x squared divided by x plus 10x divided by x. Don't get thrown off by it being a letter instead of a number. It follows exactly the same pattern. We split up the numerator terms, we keep the same denominator term. And then I look at my first term over here, 15x squared over x. Well, I just divide out one factor of x from the top and the bottom, or I think of x squared over x as being like x to the 2 minus 1 power, or x to the 1 power. That's just 15x. And then I think of 10x over x. If I wanted to, I could make this denominator like x times 1 and just divide out my factors of x. So I get 10 over 1, or just plus 10. Just having an x in the denominator instead of a 5, my procedure, my pattern didn't really change at all. My answer changed a little bit. but the pattern and the way to get there was really exactly the same. Or what if I have something like this, 15x squared plus 10x, all divided by 5x? Something that's now looking more like a monomial, 5x. Well, 5x is still just the common denominator. I can just do 15x squared divided by 5x plus 10x divided by 5x. Again, I split the numerator terms apart and put each one of them over the same common denominator term, 5x. And again, I would look at 15x squared divided by 5x. A factor of 5 can divide out of the 15, leaving me with 3, and x squared over x gives me x. That's from the first term. What about our second term? 10x divided by 5x. The x's divide out, and 10 over 5 just gives me just the constant 2. So just 3x plus 2. So don't get thrown off just because there's a variable or a monomial in the denominator, and I really ought to say x not equals 0 here. Don't get thrown off just because there's a variable or a monomial in the denominator. As long as it's a monomial down here, as long as we don't have a plus or a minus sign in the denominator, which I can't seem to select for some reason. There we go. As long as we don't have a plus or a minus sign down here, this strategy is going to work. Okay, so let's take a look at this exercise. 36z cubed plus 48z squared, all divided by 6z. So take maybe a minute, maybe 90 seconds to work through this one, and then we'll discuss the answer. Okay, so we just follow that same pattern. We break up the numerator, keep it over the same denominator. So we have 36z cubed over 6z plus 48z squared over 6z. Then we take the first term, the 36z cubed over 6z. We divide out the 6 from the numerator and denominator. 36 is 6 times 6, so we're left with a factor of 6 up top. And then z cubed over z is z to the 3 minus 1 power, or z squared. So I have 6z squared coming from this first term. And then from the second term, 48z squared over 6z. 48 is 6 times 8, so I divide out the 6, and I'm left with a factor of 8. And then z squared over z gives me z to the first. or just 8z. And I probably should say z not equal to 0 here at the end, just to make sure I respect the fact that there was a z in the denominator originally. Okay, so let's do a couple more practice problems like these. So we have 28y to the fourth plus 14y cubed over 7y squared. And again, I'm going to think of breaking this into 28y to the fourth over 7y squared plus 14y cubed over 7y squared. And here I'm going to try to do things a little bit more efficiently. I'm going to try to just work with each of these ratios of monomials separately, not really come off and write them in as scratch work, but 28 over 7, I know 7 fours are 28, so that's going to be 4. Y to the fourth over y squared, that's y to the power 4 minus 2, or y squared. And plus 14 over 7, well, that's 2. Y cubed over y squared is just y. Right, so I could do this pretty quickly once I get used to looking at these patterns. And in fact, I might even be able to skip this intermediate step altogether and just work off of this first can't think of the expression. I wanted to say equation. I was like, that's not the right phrase. The first expression here. We might even be able to skip this middle expression altogether. Now, there is a caution that I want to warn against, that a lot of folks, if they're trying to go too quickly, they become a bit careless, and they might do something like this. They might do something like divide the 7 into the 28 and get 4, and divide 2 factors of y into the y to the fourth and get y squared. And they might get something like 4y squared plus 14y cubed. And kind of, coincidentally, our first term ends up correct, but our second term is not correct. So we don't want to do this. If we're going to move along a little more quickly, skip a couple of steps here or there, we want to make sure that this 7 and y squared is getting divided into all of the numerator terms. We don't want to just divide it into one of the numerator terms and think that we've kind of gotten rid of the 7y squared of the denominator. We have to make sure that to divide it into both of them. So dividing the 7 into this 14 gives me a 2, and the y squared into the y cubed gives me a y. And now it actually works. So if I do this kind of similar process, but I remember that I need to do it to each and every term. Or kind of another way to think about this is I could think of this whole fraction here as 1 over 7y squared times parentheses 28y to the fourth plus 14y cubed. And I have to distribute into 2 different terms here. If I get a little bit fast and loose with my properties, I might make a mistake that's effectively like only distributing into one of the terms and forgetting about distributing into the second term. So I want to be cautious whenever I start skipping steps or start, not writing out everything explicitly in scratch work. I want to be careful that I'm still following implicitly those same patterns, those same rules. So I'm doing all of the same operations, but just not writing them down. If you want to do some of the operations in your head and not write them down, that's fine, but you still have to make sure that you do all of the operations correctly. Okay, so let's take a look at this exercise. 30y to the 7th plus 25y to the 5th, all over 5y cubed. And maybe try to do this one a little bit more efficiently. Maybe, avoid writing out some of that additional off to the side scratch work that we've been writing out, try to do it more or less in one line with just writing out kind of one intermediate step and then the answer. And I should have written y not equal to 0 here as well. So try to do this one a little bit more quickly. We'll take about 60 seconds or so and then discuss the answer. Okay, it's just past a minute. So when we break this into two fractions, we get 30y to the 7th over 5y cubed plus 25y to the 5th over 5y cubed. Again, make sure that you, in a sense, distribute that denominator, that each of these terms in the numerator gets divided by 5y cubed. And 30 over 5 is 6. Y to the 7th over y cubed, that's y to the 7 minus 3, or y to the 4th power. So that's from our first term, 6y to the 4th. And from our second term, 25 over 5 is 5. Y to the 5th over y cubed is y squared. So we have 6y to the 4th plus 5y squared. And again, just like similar problems previously, we note the restriction that y cannot be 0. Okay, we actually made very fast progress through all of those. I didn't think we were going to get this far this early, so we might wrap up a little bit early today. But we're now moving on to a slightly different topic. It seems like it's essentially the same problem. I have a polynomial, a sum of a few terms with numbers times x to the power over a polynomial. And I think to myself, well, I can just do this the same way, right? I can just take the same approach as up here. And I can validly do this first step. I can write this as x squared over x plus 2 plus 8x over x plus 2 plus 12 over x plus 2. That's a perfectly valid step to do. I'm allowed to do that. But the problem is, what do I do now? Right, if I look at, say, x squared over x plus 2, I might be tempted to do something like divide out an x and make this like x over 2, but that's actually not valid mathematics, right? That's not how fractions work. Right, if I have, oh, I don't know, let's say 8 over 4, I know this is 2, but if I write this as 8 over 3 plus 1, or let me write it as 8 over 2 plus 2, I can't like divide this 2 into that 8 and make this 4 over 2 or something. It actually does work out in this case, annoyingly, because I chose a bad example off the top of my head. But let's make this 12 over 6, right? If I make this 12 over 4 plus 2 and try to divide out and say 4 goes into 12 3 times, is this 3 halves? Well, no, it's not going to be 3 halves. 12 over 6 should be 2. The first example didn't work because 4 breaks in 2 plus 2, but that's the same as 2 times 2. So I picked like the one number that that I can't show the counterexample for. Um, right, but so this should be 2. It's not going to be valid to do something like this. So when I have a monomial in the denominator and something complicated in the numerator, I can handle that pretty well. I can break numerators apart in fractions pretty easily. If my denominator is simple and my numerator is complicated, I can break that into a bunch of simple over simple type problems and proceed forward from there. But here it's really my denominator that's also kind of complicated. I end up with something that's like simple over complicated, and I'm not sure what to do here. I don't want to, get stuck and then just start getting whatever careless with my properties. That's not the right way to go. We'll get an answer pretty easily, but it'll be the wrong answer. So I might go back to, say, numbers for inspiration. Let me come off to the side over here. And let me look at something like, I don't know, 172 over 9. Let's start with 171 over 9, and then we'll progress to something a little bit more complex. So 171 over 9. That's kind of what I have over here in some sense. I kind of have a big numerator, a smaller denominator, but the denominator is not trivial. So how can I figure out what I should write here? What should this be when I simplify it? What would I do? I would do long division if I was doing this by hand. And basically what I think of with long division is, okay, well, my 9, does it go into the 1 here? Basically, can 9 go into like my hundreds place evenly or not evenly? Is there enough room for my 9 to make it into my hundreds place? No. Does 9 go into 17? Yeah, it actually does. 9 times 1 is 9. 9 times 2 is 18. That's too much. It does go in one time, though. 1 times 9 is 9. And then I take 17 minus 9 is 8. I bring down my next smaller place. Right, so I had 17 tens. I put a 1 up here in the tens place in the answer. So 10 times 9 is 9 tens. 17 tens minus 9 tens is 8 tens. And then I bring down the 1 ones place, the 1 from the ones place. This gives me 81. Does 9 go into 81? Yeah, it actually does. It goes in 9 times. 9 times 9 is 81. And we get a remainder of 0. So 171 over 9 is 19. My remainder was 0. So it's just 19 even. 171 over 9 turns out to be exactly 19. If I were to look at something like, say, 172 over 9, we'd have a similar process. Does 9 go into 1? No, it does not. Does it go into 17? Yes, it does. So there are 17 tens. 9 goes into 17 one time. So we put the 1 in the tens place in the answer. 1 times 9 is 9 tens. 17 tens minus 9 tens is 8 tens. And then bring down the 2. 8 tens plus 2 ones is 82. Does 9 go into 82? Yes, it does. It goes 9 times. 9 times 9 is 81. Take away the 81, and I still have like 1 unit left to allocate. I don't have anything else to bring down, and 9 does not go into 1. So my answer is 19 plus 1 divided by 9. So I broke off a whole number, an integer bit, and then I'm left with a fractional bit. So when my remainder is 0, this is kind of like being plus 0/9, but that's just plus 0, so we just don't write it. So that's a remainder 0 case. But if I have a remainder, I end up with this vestigial little fractional part that has a numerator that's smaller than the denominator, and where the denominator is the original denominator. So 1 is smaller than 9, so I can't simplify any further. I can't break off another integer bit. And that 9, that denominator, is the same as my original denominator. How do we apply this? How do we adapt this process for polynomials? Interestingly, we can do almost exactly the same thing for polynomials. If I think of something like 171, well, 171 is just basically 1 times 10 squared plus 7 times 10 to the first plus 1 times 10 to the 0, or typically we would just write that as 1 times 10 squared plus 7 times 10 plus 1. This looks suspiciously like a polynomial, like 1 times x squared plus 7 times x plus 1. It looks suspiciously like a polynomial where we just have kind of powers of 10 put in for our x's. Or 9, I mean, I guess 9 is just 9, but if we had, say, 19, that would be like 1 times 10 plus 9. So our integers actually kind of can be broken up in a way that looks like polynomials when I take each of the places individually, multiply them by their correct power of 10, and then add them together. So this isn't so far-fetched that we should be able to treat something like this in kind of a similar manner to what we did over here. So can we do polynomial long division? So I put the numerator on the inside of my long division sign. X squared plus 8x plus 12. I put the denominator on the outside, x plus 2. Now, one little detail is it doesn't make a whole lot of sense to ask, like, how many times does x plus 2 go into x squared or something like that. So we really only focus on the leading term. We really only focus on the term that has x to the highest power, the highest degree term. In this case, that's just x. So I come over here and I ask, so here's x, and my highest degree term of the numerator is x squared. So I ask, how many times does x go into x squared? This is a similar process to asking me how many times does 9 go into 1 or 17. I start with the leading, the highest degree places and work my way over. And really what I'm asking here when I say how many times does x go into x squared, really what I mean is x times what gives me x squared. And that's, of course, just x, right? How do we figure out what the answer is? Well, I just divide through by x. Question is x squared over x, which is just x. So x goes into x squared x times. I'm going to choose to write that over the x to the first power column above the 8x, just to keep things kind of lined up nicely. Now what do? I multiply back around x times x plus 2. Well, that's x times x, or x squared, plus 2x. And I want to subtract that off. Looking at my x squared column, I have x squared minus x squared. That's 0x squared. These just go away. And then in my x to the first column, I have 8x, again, minus. Don't forget that minus. 8x minus 2x is 6x. In fact, because this negative is floating around in front of the parentheses, oftentimes what I'll do is just get rid of the parentheses and switch the sign of all of the terms. And that keeps things a little bit cleaner. Makes it a little less likely that I forget about that negative out in front. So at this point, we're kind of at this stage where 9 went into 17 once. We did 1 times 9 is 9. 17 minus 9 is 8. And then what do we have to do next? Right, 9 doesn't go into 8 anymore, or kind of the x plus 2 needs a little bit more meat to be able to go into 6x. Well, I would bring down maybe I won't put an x there. I'm going to put a check mark. So it doesn't, I don't want the x's to get confused with variable x's. But I put a check mark under the 12 and bring it down, 6x plus 12. And then I repeat the process. I look at my new highest three terms, x and 6x. I ask how many times does x go into 6x, or in other words, x times what gives me a 6x. Of course, that's just 6. 6 times x plus 2, well, that's 6 times x, or 6x, plus 6 times 2, plus 12, and I'm subtracting that. And here I actually see that I get something minus the exact same thing. That gives me 0. So nicely enough, my remainder equals 0 in this case. So x squared plus 8x plus 12 over x plus 2 gives me x plus 6 with a remainder of 0. Now we can actually check this. I'm actually going to go up above to check it because we've got a bit more room up there. We can check this, right? If my claim is that a over b equals c, I should be able to multiply both sides by b. And it should be that a equals c times b. Or my claim is that x squared plus 8x plus 12 over x plus 2 equals x plus 6. I should be able to multiply both sides by x plus 2. It should be true that x plus 2 times x plus 6, when I multiply that out, I should get exactly x squared plus 8x plus 12. Let's check. My first give me x times x, or x squared. My outsides plus 6x. My insides plus 2x. And then my last plus 12. That looks like 8x, and I have x squared plus 8x plus 12. So I've checked my work. My answer is x plus 6. So we can actually divide polynomial by polynomial now. Remember, dividing polynomial by monomial is pretty straightforward. We just kind of have this strategy where we break everything apart into monomial divided by monomial and just simplify all of our quotients of monomials. That's whenever our denominator is simple, but the numerator might be complicated. We follow this strategy. But when our denominator is complicated, when our denominator has more than one term, it's not just a monomial, we're going to do something more like this, like polynomial long division. All right. Any questions on this? So we actually made pretty good time today. I don't really want to bite off much more than this. I don't want to do much more than an introduction to this topic because we've already done a lot today with ratios of monomials, and and I don't want to throw any more of what I had planned for next lecture really on top of what we already learned today. I think we've already covered a good chunk of material. So we'll pick up with this topic next time. I would recommend before next class, taking a glance through this section in the book and maybe working through a couple of the examples in the book, working through it alongside the book, working alongside the book with their solution to go through this process a couple more times, right? It's not it's not a strategically like difficult process. It's not one of those processes that's like at every step of the way you're trying to figure out like a puzzle what to do next. But it's one of those things that, just the first couple of times you go through it, you're not really sure what to do at each step. And then the next couple of times you're pretty sure what to do at each step. And then by the 10th or 12th time you've done it, it's just more algorithmic at that point. It's just kind of like turning a crank and working through until you get to the end. So going through these examples like this a couple more times before next time will make this an easier lecture next time. Any questions on anything from today? Okay, let me stop the recording.